I have previously made a video similar to this, but I would like to do it with a more modern status of knowledge, and also try to do it without any mathematical terms, nothing wild or crazy, and no misinformative theories. And also, at the same time, within under 5 minutes. This is more of a challenge than anything else, really, but it's only so difficult because, imagine a bunch of people dawdling around saying, well, we know there is this magical invisible force that pulls objects toward each other, and then taking a bunch of pictures of nothing and making a whole thesis on it. It's tough stuff out here in the universe, but it's even tougher trying to understand what wasn't made to be understood, which is why I would like to do my best. So, physicists have tracked and traced and even controlled 3 of the 4 current forces, the electromagnetic force and the strong and weak nuclear forces. But the 4th fundamental force is gravity. It's different, but how? Well, what makes it so dominant in the current universe? Well, to understand what it is, we have to understand what it isn't. The lovely process of elimination. So what do these 3 have that gravity doesn't? Well, we can compare it. Electromagnetism is an incredibly strong force, but it can only be present with 2 opposing signs of charge, positive and negative. Its incredible strength in small quantities and ability to be controlled using current gives it so many appliances in our daily life, and it's so usable on a human scale, right? Yeah, this is all human-sized stuff. Electromagnetism's range can scale and warp, depending on the amount of charges present and the intensity of current. And the strong and weak nuclear forces function the exact same, except they are limited to a range of roughly the size of an atomic nucleus. So, one is really powerful and large, and the other 2 are even more powerful but very tiny and finite. Well, gravity, it throws all of that out the window. This is where the problem lies, right? Gravity has an infinite range, meaning it affects objects no matter how far apart they are, right? That's stage 1, out the window. Gravity is a force we can't escape. Stage 2, out the window. It does not repel like magnets do, it only attracts. Stage 3, out the window, and requires only an existing mass or energy to be present. Gravity is simply just universal. Of course, still being classed logically as a force, it is a force with which each and every body in the universe with a mass attracts all other bodies having a mass, regardless of their size or composition. In a summary of Einstein's theory of general relativity, space-time is essentially warped by mass or energy. So basically anything great enough to cause this effect would just end up making a big old bend in space-time. The reason we're standing on Earth, the reason our sun is always so perfectly distant, and the reason the universe makes anything the way it does to this day. This is the real fascinating part, and yet it's also stupidly weak. All things considered, this thing that we're standing on weighs 6 times 10 to the power of 24 kilograms, with a relative uncertainty of 10 to the power of -4. It isn't just slamming and crushing us all into the surface and killing us with raw force. It's pretty pathetic, honestly. But no, we love it, we need it. I'm joking, I do love gravity. Weak or not. But when I say it's universal, I mean universal. Anything with any amount of mass, regardless of its composition. So, what I'm saying is that at any scale, of any size, in any moment in the universe, gravity is always involved, even if it is to do with the smallest possible number of 0.infinity newtons. It is present, and interacts with even something as small as photons, and even gluons. These are essentially the thing that holds quarks together. So I'm just saying that for dramatic purposes, but of course, gravity being stupidly weak, it does absolutely nothing to these things, because it scales, right? Scales based on mass, and gravity is so predictable, but we just can't fathom what isn't really in front of us. We don't have a quantum theory of gravitation, we can't just determine its gravitational field or effect. If you're lost, I will give a new perspective of everything in the quickest terms, using the current theories of the day. In a very dramatic sense, gravity caused the original gaseous matter in the universe to interact with itself. Gravity was too weak to contain the eventually monstrous manifestation of matter and energy, and it had released a burst of pretty much everything that could possibly form. From stars, which eventually condensed into galaxies, to microsecond black holes that could potentially have been the size of atoms. The beginning, middle, and end of the universe's history will and forever be entirely reliant on gravity. It is gladly responsible for many of the finite and large-scale structures in all of the universe. Although I'm being a little dramatic, it is still infinite, although its effects become weaker as objects get far away. T's and C's apply. Gravity is most accurately described as the curvature of space-time caused by uneven distribution of mass, and causing masses to move along geodesic lines. That basically means the quickest path between 2 points. The most extreme example of this curvature of space-time is a black hole, from which nothing, not even light, can escape once past the black hole's event horizon. Oh, and fun fact, the reason a black hole's accretion disk can be seen from 3 points is because it warps space-time so intensely that its light is actually bent up and over the black hole. Sorry, but we can't go around testing these things because we need such large-scale masses and energy. We can only theorize. Therefore, I do not want to misinform you all on its wonders, but I hope I have informed you well either way. Gravity remains the great cosmic mystery.